let's start. We have David Gabai telling us about shrink-wrapping, taming hyperbolic 3 manifolds. Other people have said, I mean, there's just so many things that that Dennis has sort of contributed to, that's sort of impacted the right. There's just so many things that Dennis. Right. So there's just so many things that Dennis has done that has sort of impacted sort of the mathematics that I've been involved with. So in particular, I spent basically the first 8 years of my life only thinking about taut foliations. And I mean, the fact is that as far as I know, Dennis proved the first theorem in the subject. He just proved this really beautiful theorem that if you have a, well, stated in the context of three-dimensional manifolds, if you have a three-dimensional manifold and you have a foliation, codimension 1 foliation, which is C2, and then it's taut, that is, there's a curve. Say it's a foliation in a closed manifold, then there's a curve that's transverse to all the leaves, if and only if there's a Riemannian metric on the manifold such that each leaf is a minimal surface. And anyway, that's just a really beautiful and fundamental theorem. And actually, my understanding is that in the same paper, Dennis, so has a generalization of that basically to all, appropriately to all dimensions and codimensions. But I mean, I only, it took me 8 years to have a little understanding of just the three-dimensional case. So, but anyway, that's just a really beautiful theorem. And as you heard in the previous lectures, just the other, really tremendous impact. So I should say that I'm also really kind of lucky Dennis is showing up for this lecture, because I gave a lecture about maybe 5 years ago or so at Frank Quinn's 60th birthday, and I talked about tameness, and Dennis was there, and after the lecture, he just really chastised me, and appropriately for not really making clear sort of like Bill Thurston's sort of enormous contributions to the subject. So hope, and also he didn't say it, but it was maybe a little bit incoherent, the lecture. So it's really lucky in life where you sort of get a second chance. So hopefully in this lecture it will be, one, a little bit more coherent, and two, maybe I can make a little clearer sort of just the huge contributions that Bill made to the subject. Now I was asked by the organizers to talk about the tameness theorem, but there was no restraint on. I wasn't. I mean, Hausdorff dimension didn't come up. I wasn't asked to talk about Hausdorff dimension. So therefore, I feel free to give an example of a non-tame manifold, and this is famous, well, basically correction to a very famous mistake of J.H.C. Whitehead. And in 1934, Whitehead more or less published a paper purporting to prove the Poincare conjecture. And the idea was that if you have a homotopy 3 sphere, then you delete a point, and what's left is a contractible open 3 manifold. And in this 34 paper, he proves that that all contractible open 3 manifolds are R3, and then that's the way to proving the Poincare conjecture. but then he quickly realized his mistake, and well, actually within 6 months or so, he sort of published this example of an open contractible three-manifold that wasn't R3, and it's known as the Whitehead manifold. And this manifold, as you can see, well, as I've written here, it's the increasing union of solid tori. So you take one solid tori, embed it in the next, embed it in the next, and so on and so forth. And so here's the first solid torus. It's embedded in the second, and the second's embedded in the third in the same way, and the third's embedded in the fourth in the same way. And so you can see that here's the embedding of the first and the third. But the point is that the image of the first one is sort of this curve, and you can see that the inclusion of like the first solid torus in the second could be contracted in the second to a point. So and in general, the inclusion of the nth and the n plus first. So any map of a so if you want to compute pi n of the space, then a map of a sphere, it's compact, so it lives in some nth solid torus, and then you can see already it could be contracted in the n plus first solid torus. So anyway, so you could see that, well, at least pi 1 is trivial, and actually you could just, well, I mean, all the homotopy groups are trivial. So therefore this space, and Whitehead also showed that for CW complex that if all the homotopy groups are trivial, then it's contractible. So anyway, this is a contractible three-manifold, but the reason why it's not R3 is because it has the property that if you look at the Whitehead manifold and then delete the first solid torus, then what's left is some manifold which has infinitely generated fundamental group. And well, that's certainly not the situation if you're in R3, because if you have any smooth submanifold of R3 that's compact, then if you just take some very large round ball, that submanifold will live in that ball. So therefore, if you delete that submanifold like C, then what's left is just a smooth compact manifold. So it has finitely generated fundamental group, but now, I mean, you're just adding on sort of the outside of the ball, which is like a S2 cross half open interval. So that doesn't change the fundamental group. So you could distinguish this space from R3 because here's a smoothly embedded compact submanifold, infinitely generated fundamental group in the complement, and this one doesn't. I mean, R3 doesn't. So actually, this example is a method of generating all sorts of examples. So I guess Macmillan in the 60s showed that this type of construction leads to sort of an uncountable number of contractible open three manifolds, or contractible open three manifolds that are not homeomorphic. And in general, you could get all sorts of contractible, you can get all sorts of exotic manifolds. I mean, if you, instead of just mapping in homotopically trivial, but you map in sort of an interesting manner, but it's just homotopically just going around once, and the inclusion of the second into the third just homotopically goes around once, but geometrically sort of links around multiple times. You do that repeatedly, then you'll get a manifold which is homotopy equivalent to an open solid torus, isn't an open solid torus. And so in this manner, you get lots of examples of homotopy handle bodies of any genus and uncountably many such things. So, right, and actually, sort of as a variation of the theme, let me just, just mention is, so this Fox-Artin manifold. So this manifold is a submanifold of R3, where here's this green curve. You could see it's sort of this knot that sort of just well, it's a sort of a knotted ray in R3, and now just thicken it up and take its interior, and now take this ray, thicken it up, and just delete the interior, and you're left with a manifold with boundary. And it's easy to see that, well, it's a little exercise, that topologically, what the interior of this manifold, so if you just delete this closed neighborhood, the interior is just an open R3, and as the manifold with boundary, the boundary is an R2. So here's a manifold with boundary, interior R3, boundary is R2, but this manifold's not homeomorphic to the standard R3, R2 pair, by which I mean the closed upper half space. And again, it sort of has sort of the similar feature that Whitehead observed, is that if you sort of just delete from this manifold just this arc, then what's left is a space with infinitely generated fundamental group. And actually, Tom Tucker showed that actually characterizes sort of non-tame manifolds, that a manifold is non-tame if and only if, in appropriate sense, if you just delete any smooth, compact, suitably embedded submanifold, then what's left is, so manifold's tame if and only if every time you just delete some smooth, compact thing, then what's left is has finally generated fundamental group. So, right. So here's a definition that so Dick made clear in the last lecture, is that, just stated in slightly different words, is that a manifold, or even a manifold with boundary, is tame if and only if it's sort of has a manifold compactification. So in the context of an open manifold without boundary, the manifold is tame if it's the interior of a compact manifold with boundary. So possibly boundary is empty. So right. So here's the topic for discussion. Is this theorem, is that if you have a complete hyperbolic three-manifold with finally generated fundamental group, then this manifold is both geometrically and topologically tame. So topologically tame is, as I said, means that it's sort of be compactified to a compact manifold with boundary. And actually, Dick Canary mentioned what it means to be geometrically tame, and I'll mention that a bit later. And actually, Dick gave a quick argument why his theorem, 1990, that is that if you have a hyperbolic three-manifold that's topologically tame, then in fact it's geometrically tame. So let me just mention very briefly just some history, that there's a lot of interesting partial results in the subject, and I highlight sort of 4 of them, and then I mention just various authors, and maybe I'm sure I've left people out, but I mean, Marden, to start with, he formulated this conjecture, and in particular, as he thought about things geometrically finite a little bit differently, but he proved it for geometrically finite, and Thurston, proved it for certain algebraic limits of quasi-Fuchsian groups, and Francis Bonald showed it for when the group couldn't be written as a free product, and Juan Soto for manifolds with nice exhaustions. And well, in all these cases, it's more so the elements that sort of went into understanding them were very influential in the final resolution, at least from the point of view of Danny Calegari and myself. And right, and then there's, as Dick went into sort of more detail, then there's sort of a lot of other interesting partial results. And so here's some references that sort of there's, I mean, the original papers of Ian Agol and Danny Calegari and myself, and Teruhiko Soma. Well, as mentioned in the introduction, there's this idea of shrink wrapping, and we did it in sort of in the smooth category, and he found sort of, well, what he calls these polygonal wrappings, and sort of drastically sort of simplified the argument of existence of shrink wrapping. And I don't know so much about this, but I believe it's sort of based on sort of what Ian Agol did. And then Brian Bowditch has sort of more notes on tameness, so that someone could sort of exit, 1978 and wake up in 2010 and be able to just understand tameness. And anyway, I wrote some notes that based on Park City lectures, which based on sort of the work of Danny and myself, incorporating some big improvements of Soma and Bowditch. So, right. So, but before I start, let me just mention this, which is that there's some cases where this tameness is very simple, where if the manifold already has trivial fundamental group, then by the Cartan-Hadamard theorem, I mean, since sectional curvature -1, then it's simply H3. And by classification of isometries, then if the manifold has fundamental group Z, then it's just an open solid torus. But if you just take it to the next step, which is the manifold is Z star Z, a free group of rank 2, well, it turns out that was just basically the most problematic case. So here's an important sort of topological thing that went in, and which Dick already mentioned, which is the Scott-Core theorem. And that says that if you have an irreducible three-manifold with finitely generated fundamental group that's connected, then there's this compact submanifold that has the property that living inside the manifold, which is where the inclusion is a homotopy equivalence. So schematically, it's sort of this picture where here's sort of the three ends, and here's the compact core. And an end is something like various things in life that are sort of kind of difficult to actually just explain precisely, but when you see one, you recognize it. You know what it is. So it's the same sort of thing, is that you could just the first approximation, and really for this discussion it's good enough, is to think of an end as just a component of M, of M minus the compact core. In other words, there's a one-to-one correspondence between the ends of the manifold and the boundaries of the convex core. And these boundaries that are sort of facing out to the core, think of those as the ends. And just quickly mention what Dick said, is that there's ends of hyperbolic three manifolds of two varieties. There's the geometrically finite type and the geometrically infinite type. And geometrically finite, well, the way we think of them now is, already the ends are just flaring out exponentially, and they have nice product structure. And then there's everything else, which is what are known as geometrically infinite. And so, as Dick mentioned, that the canonical example of a geometrically infinite end is you take a manifold that fibers over the circle, and you just take its infinite cyclic cover, and sort of the ends of this infinite cyclic cover are geometrically infinite. So here's an important fact that due to Francis Bonahan, characterization of geometrically infinite, is that a space, the end is geometrically infinite if and only if you can find a sequence of closed geodesics that are exiting the end. That is, you could find a sequence of closed geodesics sort of living in the end with a property that for any compact set, only finitely many will hit that compact set. So, and actually, just with a little cut and paste argument, you can actually assume that all these geodesics are simple and they actually have a certain amount of separation from themselves and from each other. So in particular, you could put like little tubes of definite radius about each such geodesic. So that's sort of a starting, an important fact that will play a role in this discussion. So now I want to tell you a couple very basic facts about hyperbolic 3 manifolds. And actually, before I start, let me just say that just to get to the heart of the discussion, I'm going to assume that the manifold has no parabolics. And so in particular, there's no cusps. And I should mention that actually, in the cusp case, there's a theorem of Dennis plays a role, and there's the Sullivan finiteness theorem for cusp manifolds. That if you have a 3 manifold complete with finitely generated fundamental group, and then there's only the parabolic. There's only finitely many components to the parabolic locus, and in the cusp case, that sort of plays a role in the beginning of sorting out the ends of manifolds with cusps. But for today, we just talk about manifolds with no parabolic elements, and in that case, there's the Margulis thick-thin decomposition, which is very simple. As a very simple statement. That is, you have your hyperbolic manifold, then this manifold can be basically decomposed into sort of two things. There's the thick part, and those are parts where every point in the thick part has sort of injectivity radius sort of bigger than some universal epsilon. And then there's the thin part, which is sort of everything else. And those are simply solid tori that are sort of neighborhoods of short geodesics. So you should think of for complete hyperbolic manifolds, you have these solid tori which sort of enclose all the short geodesics, and there's sort of the rest of the manifold, which consisting of points with sort of some uniform bound and injectivity radius. And there's a second crucial thing, which is called the bounded diameter lemma. In my mind, this is sort of the miracle of Gauss-Bonnet. And, it might not seem like a miracle right now, but hopefully I'll try to convince you it really is. Which is, it's a very simple fact that in its simplest form is, suppose you have some surface whose intrinsic curvature is less than or equal to -1. And you have a surface of some fixed genus. Then by Gauss-Bonnet, its area is bounded above by 2 pi times its Euler characteristic, or absolute value of Euler characteristic. So since there's a lower bound in injectivity radius, there's basically just a uniform number the surface is covered by uniform number of balls of some fixed radius. So therefore, if you have any in a hyperbolic three-manifold, a surface whose intrinsic curvature is less than or equal to -1, and it has a lower bound on injectivity radius, then its diameter in the manifold is sort of uniformly bounded above. And more generally, if there's sort of short curves in the surface, if the injectivity radius is small at some points, well then all that stuff lives inside the Margolis tubes. So the bounded diameter lemma says that a surface with intrinsic curvature less than or equal to -1 hyperbolic three-manifold modulo the Margolis tubes has bounded diameter. Or said another way is that given any 2 points in the surface, if you just say draw a line in the manifold, then the part lying outside the Margolis tubes is uniform bounded length, and actually, and furthermore, actually, that the surfaces that we'll be dealing with will only be intersecting a uniform number of Margolis tubes. I mean, at most, some finite number. So, right, so I mentioned this word cat -1 surfaces, and actually Dick talked about it in his lecture. So there's various sort of equivalent ways, or more or less equivalent for the purposes that at hand, to think about surfaces in three manifolds which have intrinsic curvature less than or equal to -1. And one is minimal surfaces, surface mean curvature equal to 0. Pleated surfaces, these are geodesically embedded surfaces that are, geodesically immersed. These are immersed surfaces. Well, I meant to say immersed, which well, they're not smoothly embedded. They might be bent along geodesics. And then there's sort of simplicial hyperbolic surfaces that are sort of piecewise geodesic. They have triangulations where each triangle is mapped in totally geodesically, and has this condition that around every vertex the cone angle is at least 2 pi. So it's constant -1 curvature except at vertices where there might be some concentrated negative curvature. So, right. So basically, what you really need to know is sort of thick-thin decomposition and bounded diameter lemma for what I'm about to say. So, but before I say that, let me mention just what I call Thurston's tameness theorem, and which plays an important role in this discussion. And Dick sort of mentioned it in his lecture. And that is that, actually he mentioned it at the very end of his lecture, and that is, suppose you have a compact three-manifold that's irreducible and atoroidal. So there's no essential, there's no z plus z subgroups in the fundamental group of this manifold. And suppose the boundary is non-empty, and furthermore, there's some component of the boundary that has sort of negative Euler characteristic. Then if you consider any subgroup which is finitely generated, the fundamental group, and you look at the covering space of this manifold corresponding to that subgroup, then that covering space is topologically tame. And as Dick mentioned, in the 70s, people worked really hard to do some very special cases. And as sort of a consequence of Thurston's hyperbolization of Hawken manifolds, is there sort of a very, it's a simple, relatively simple consequence of it, is that given such a manifold, then Thurston can put a geometrically finite structure, and the fact, it's a little fact that finitely generated subgroups of geometrically finite groups are geometrically finite. And we saw Dick explained that geometrically finite manifolds are tame. So that's Thurstons' tameness theorem. Yes. So the Euler characteristic of the manifold is like half the Euler characteristic of the boundary. So one's negative, the other's negative. So the Euler characteristic of the manifold is negative, for irreducible, if and only if there's some component of the boundary which has negative Euler characteristic. So another crucial ingredient of Thurston is what I call Thurston's tameness criterion. And Thurston's tameness criterion, is a manifold satisfies, n satisfies this criterion if, if it satisfies two properties. Well, first is that the end is homotopy equivalent to a surface. So in this particular case, like here's the end, and here's the boundary of the end, the surface. So the first condition is the inclusion of the surface into the end is homotopy equivalence. And the second condition is that there's a sequence of in Thurston's terminology, there's a sequence of pleated surfaces that are exiting the end. That is, for any compact set, there's only finitely many of these surfaces that hit the end. So another way of saying this is, as I mentioned, that there's different ways of thinking about surfaces in Q manifold intrinsic curvature minus one or less. So we should think of, so another way of saying this is that there's a sequence of surfaces that exit the manifold whose intrinsic curvature is less than or equal to minus one, and have the feature that these immersed surfaces are homotopic to sort of this base surface. And Thurston, called such an end sort of a simply degenerate end. And so an end which has this property is known as geometrically tame. And actually, technically, a geometrically tame end is one that's either geometrically finite or has sort of this property. And I call this Thurston's tameness criterion because Thurston, at least outlined how if you had an end which satisfied these two properties, then the end is actually standard. That is that the end is actually homeomorphic to surface cross zero infinity. So here's here's sort of Thurston's outline. And Thurston's outline was this: is that if you have this sequence of these intrinsic minus one curvature surfaces exiting the end, then you can use this technique, which he called pleated surface interpolation. Let's just simply call it surface interpolation, to find a proper map of S cross zero infinity into the end, which takes S cross zero to this surface over here. And then sort of, hinted at a topological argument that if you have such a proper map, then the end is actually homeomorphic to S cross zero infinity. So, and I should say that in Francis Bonahan's work on indecomposable manifolds with indecomposable fundamental groups, it gives a nice clean proof of this tameness criterion implies that the end is actually tame. And I should say that his proof in an essential manner, uses that the end is homotopy equivalent to surface cross R. And right, and maybe just as a historical note for is that there's these different ways of thinking about there are these different ways of thinking about.
The previous slide?
Oh, the previous slide. Yes. So just as a historical note, that Bill sort of thought about pleated surfaces, but sort of in this sort of mysterious paragraph, he makes it clear that he also thought that there was a way to think about this in terms of what's now known as simplicial hyperbolic surfaces, and as he says that that although his approach involves a more familiar method, the author brutally chose to develop extra structure. And in this section, this is written in chapter 9, the section he developing pleated surfaces just develops this beautiful, further developed this beautiful theory of laminations on surfaces. So there's Thurston's tameness criterion, and so here's our taming criterion. So Danny and I did, and which is actually just an epsilon. Well, okay, so here it is. Suppose you just take any end. I mean, just draw this picture as if the manifold is one end of a hyperbolic 3 manifold, and now you don't know any about the homotopy type of the end, but you know three things. One is that you have the sequence of intrinsically curved surfaces -1 curvature exiting the end, and two is there's this genus bound that the genus of these surfaces are not any bigger than the genus of this surface, which is the end of the Scott core. And the third condition is that these surfaces are homologically separating the end from infinity. So if you just draw any ray going out from the end, then that ray will at least intersect these surfaces with positive algebraic intersection number. So, and notice that this is sort of very similar to Thurston's tameness criterion. You have the exiting surfaces, and replacing by, being homotopic to this base surface implies that it's sort of homologically separating. And I should say that if you actually drop the second condition, that Juan Soto more or less sort of proved this. I mean, for some reason he required this extra hypothesis that the manifold not have free fundamental group, but more or less this argument using Dick's branch cover, great branch cover idea. And also using the fact that the Thurston norm is equal to the Gromov norm, he was more or less able to prove this under conditions 1 and 3. But sort of I like to, just that plus a little epsilon, you can just prove this criterion is good enough to prove tameness. So now I'd like to give you an idea of the proof of the tameness theorem. So we want to show that there's a sequence, show it satisfies this tameness criterion. So let's give a proof of Dick's theorem that if you have end of a 3 manifold that's ends topologically tame. Sorry, if topological tame implies geometrically tame. So topologically tame implies geometrically finite, or it in my language, satisfied the Thurston taming criterion, but which is just the same as being geometrically tame. So what we need to show is that if you're topologically tame, then there's a sequence of surfaces of intrinsic curvature -1 that exit the manifold. And here's the proof. I mean, just stare at this picture. I mean, so here's the proof. I mean, that look at the case where the manifold just surface cross R. Now, if it's geometrically infinite, Francis says there's a sequence of geodesics, closed geodesics, that are exiting the manifold. So now we know that, I mean, since the end's tame, then we could just look at a sort of a section of the end that's sort of really far out. So if we just look at the 1000th geodesic, then we look at some surface, after the 1000th geodesic, or here. I mean, didn't draw 1000. I draw like 1, 2, 3, 4. But so here's a surface that's after the second geodesic, but before the third, like this one here. So what you do is you simply shrink wrap the surface. So what I mean is that you go to the the supermarket, and you go to the freezer section, you see these turkeys, and the turkey is sort of in this bag, and the bag is like pulled tight. So the bag is more or less like a minimal surface, subject to the condition that it sort of can't go through the turkey. So that's what shrink wrapping is. That you take your surface and you shrink wrap it with respect to these geodesics. So here's a surface. It's sort of like stuck between these two geodesics, and then you shrink wrap it, and when you shrink wrap it, it becomes a surface of intrinsic curvature -1. I mean, the turkey has these elbows, which are sort of points of positive curvature. But somehow, if the boundary of the turkey was negative, well, at least straight, then when you shrink wrapped it, at least it wouldn't have points of positive curvature. And so you're shrink wrapping with respect to these geodesics. So when you pull this thing tight, this thing has intrinsic curvature -1, and there might be these points of where it's sort of along these curves. Now, the point is that so why does this satisfy the taming criterion? Well, I mean, they have the right genus. Their intrinsic curvature -1. I mean, by construction, they're homologically separating. The big thing is, why do they exit? But they exit because that if you go out to the surface at sort of a thousandth one out, all the way out here, well, by shrink wrapping, it's sort of like stuck between this curve and that curve. So there's if like you drew a little arc from this curve to that curve, when you shrink wrapped it, it still had to at least geometrically hit that curve. But on the other hand, there's the bounded diameter lemma, which says that, well, modulo the Margulis tubes, and it will only hit finitely many of them, is that the surface has bounded diameter. So if there's part of the surface that's sort of stuck out here, the bounded diameter lemma says that it really can't go, it can only go back sort of like a limited distance. So, the point is the Margulis tubes are sort of discretely placed, so you just go far enough out that you can only go back so many Margulis tubes that you could see these guys just don't come back. I mean, if you go out far enough. So this in particular shows that satisfies the taming criterion. So therefore, it's geometrically tame. So right. So let me just say more precisely about shrink wrapping. So it's a way of finding intrinsic curvature -1 surfaces in 3 manifolds, and basically the shrink wrapping theorem. So there's this technical thing which says that if you have a map of a surface which is not necessarily incompressible, but it's what we call too incompressible, then you can shrink wrap the surface. So So I mean, there's the theorem, I guess, Meeks and Yao, Shane, and that Meeks and Yao says that if you have like an incompressible surface in a Riemannian manifold, then you can homotop that surface to be a minimal surface. And the condition really is that there's no simple closed curve on the surface that's homotopically trivial. Now here, you're dealing with surfaces and handle bodies, so everything's compressible. But if it satisfies, but on the other hand, you're shrink wrapping. So the thing is that if every compressible curve intersects every geodesic at least twice, that's what I call it. Such a surface would be too incompressible. So here's a standard compression, like a 1 compression, 2 compression. So the shrink wrapping theorem is sort of just as I've sort of hinted at in this picture, is that if you have a surface that satisfies this incompressibility condition with respect to these curves, then you can shrink wrap it. And furthermore, it's only when you're doing this homotopy, at the end you get this intrinsic curvature -1 thing, but you only hit that thing sort of at the last moment. And again, as sort of I tried to explain why these things sort of exit, is because of this simple principle is that geodesics trap surfaces. So if I'm shrink wrapping this surface, and on one side is this curve and the other side is this curve, and just draw any arc, then when you shrink wrap it, well, who knows? It might want to jump this way or that way, but the fact is the shrink wrap surface is going to intersect that arc. And the shrink wrapping theorem. Shrink wrapping theorem. So, right. So, yes. So, right. So let me try to now explain sort of the general case of Dick's theorem, how this sort of works there. So here, here you have maybe you have a hyperbolic few manifold that say is a homotopy handle body of say genus 7 or something. Genus 16, there it is, genus 16, and now you try to play the same idea. Well, again, by Bonnemann, there's a sequence of closed curves exiting the manifold, and then you want to just find a sequence of surfaces that exit that are homologically non-separating. So here you just take this section, like surface cross 7, and you shrink wrap it. Now here you might run into a problem because shrink wrapping, you have to avoid, the thing has to be incompressible, and there's no reason why the surface, even though there are these geodesics here, when you compress it, you might actually do a compression, or furthermore, you might be there like there's a 1 compression. You might do a compression that intersects this, the geodesics at 1 point. But the point is, okay, so that happened to surface cross 7. So now you look at surface cross 10,000. Now you see like there's 10,000 guys in here. And you say, okay, well that's probably okay. But no, I mean, the fact is that this thing could be compressible and maybe actually topologically look very similar to sort of this picture. But the thing is this, is that you should think of these geodesics as, well, as sort of like flies in this bag here. They're sort of like flying around, and a compression, you just compression up, you miss the fly. So you compress the fly, that happens. But the point is that this is a surface of genus 16. So that can only happen maybe 30 times or something. So, and furthermore, well, okay, the bad thing is you can do a compression, you can like squish one of the flies. Okay, but the fact is, if you hear it like 10,000, then when you when you sort of did these 0 and 1 compressions, you might have, okay, got the same qualitative picture. But there's still, you know, like 9,970 sort of geodesics left in here that haven't been sort of squished. So, right, so this looks sort of problematic. So anyway, just to simplify matters just so slightly, is that you should think of this as sort of like a bag. And you know, like a balloon in here, and there's stuff flying around, you squeeze it, and sort of the bag gets maybe a little smaller. But the point is that maybe a little pigeonhole principle is that, well, after passing to a subsequence of these surfaces going out, that you could always assume there's some particular geodesic, let's call it, say, delta P, that lives in every bag. And furthermore, the bag contains sort of an awful lot of these geodesics. So in particular, any bag, you know, has sort of this particular geodesic delta P, but then sort of like this furthest one out, it's called delta P sub I. On the other hand, there's geodesics to the far side, to the outside. Now to each of these geodesics, you can imagine like drawing a ray going off to infinity. So to each geodesic, there's, you know, so you have this, you know, locally finite collection of rays. So now you shrink wrap. We say, okay, well, look, this looks like a, you know, kind of bummed out because of this picture, but you just not worry about it. You shrink wrap it anyway, and okay, you shrink wrap it, and here's sort of now the shrink wrap picture. But now you remember, oh, there's the miracle of Gauss-Bonnet, which is that there's the bounded diameter lemma. I mean, what I mean is that here's this shrink wrap surface, and inside this surface was this curved geodesic delta pi, which is very far out in the manifold. And there's this ray going off to infinity. So when I did the shrink wrapping, this surface has to hit this ray. But so the surface is going to have to be pretty far out. On the other hand, it just can't escape to infinity because it's trapped, because it's delta I plus 1. So the real picture is that because of the bounded diameter lemma, that this surface actually has to be very far out in the manifold. And so the shrink wrap surface has to be very far out in the manifold. And furthermore, being far out in the manifold means that it's disjoint from this curve delta P. So therefore, to start with, delta P being on the inside had algebraic intersection number 1. I mean, looking at a ray from this guy to infinity with this surface, it's still going to have that property, you know, well, by the shrink wrap theorem, it's going to have that property with this sort of final surface. And in particular, there's this guy so far out in infinity, there's a little path from the core to this curve, which is disjoint from him. So therefore, since this ray has algebraic intersection 1 with this curve, then therefore this core is, if you look at a ray going out from the core to infinity, that one still has the algebraic intersection 1. So therefore, the upshot is that really this picture couldn't have happened, that in fact this surface, the shrink wrap surface, actually is very far out, and its genus might have dropped, but actually it couldn't have dropped for algebraic topology reasons, and it's homologically separating. So therefore, these shrink wrap surfaces are the surfaces that you wanted. So, right, and you know, I've got 5 minutes left or so, and I've succeeded in explaining why a manifold that's topologically tame satisfies the tameness criterion. So, but the general case for 3 manifolds, for general hyperbolic 3 manifolds is just sort of a mild sort of generalization of this idea. So, well, I don't really have much time, but let me just sort of throw out sort of just some pictures here. So in a general, and here now this is just pure topological, is if you just have some 3 manifold, and let's just assume already the manifold, just for simplicity, is to start with already as just a homotopy type of its fundamental group is just say a free group of rank 3, and you just have a sequence of just simple closed curves exiting the manifold, then there's sort of this like engulfing type idea that's based on this theory of end reduction due to Bryn and Thurstons, which more or less says that there's this sort of open submanifold which sort of engulfs these curves. Now, and well, it has some other important properties. In particular, this submanifold, which is the union of these WIs, well, it H1 and pi1 injects into the ambient space, and furthermore, each of these it has that submanifold in turn has sort of an exhaustion by compact sets where, say, in the third set, the third geodesic is could be homotop to the core of this sort of submanifold, and so. But this is just purely topological. But if you add but if this is actually happening in the world of hyperbolic 3 manifolds, then if this was actually an end of a hyperbolic 3 manifold, and these were geodesics, then these WIs turn out to be like atoroidal compact 3 manifolds. So, right. So if you just look at it just, qualitatively, this picture is very much like the picture in the proof of Dick Canary's theorem. The only difference is that already here these surfaces that, I mean, their genus is probably going off to a billion, and first of all, they're not, in general, not even these topological surfaces, are not exiting the manifold, and there's certain topological examples where they distinctly can. But nevertheless, you shouldn't worry about that. So, but the point is that, but nevertheless, we still can sort of, think along those lines. Where here's maybe the W10,000. You can see 10,000 geodesics, and here's sort of the core, not of the manifold, but of this sort of end reduction thing. But actually, the genus of this, if this is a free group, this could be a free group of not any larger rank. So, right. So I'm running out of time here, but so here's some words, and so here's where Thurstons' tameness theorem comes to the rescue, where so the point is that here, maybe I shouldn't even look at this picture. So here it is in the ambient manifold, and here's sort of like this surface cutting off like a piece of the end reduction, and here you have like 10,000 geodesics. Now the question is, I want a surface of genus 3, not a surface of genus 10,000 to shrink wrap. It's not going to do me much good if I shrink wrap this 10,000 guy. So how do I find a surface of genus 3? Well, simply this. This manifold here is a compact manifold which is atoroidal. And now we apply Thurstons' tameness theorem to what subgroup? Well, to this manifold, to the subgroup, this subgroup of rank, this subgroup which is the core of this end reduction. And so we pass to the cover corresponding to this rank 3 subgroup, and well, here it is. It's sort of like this funny looking thing, and here this thing becomes the ends of this manifold, whatever it is. But Thurstons' tameness theorem says that the interior of this covering space is topologically tame, and we know what the homotopy type of this thing is. The homotopy type of free group of rank 3. So therefore, this thing over here is actually just push the sort of the compactification in a little bit. Here is a surface of genus 3, and now you just run through this argument that we had in the proof of Dick's theorem, where now you just look at this guy and you do sort of maybe you have to do like 0, 1 compressions, but again, there's like 10,000. Well, again, part of the business with the end reduction is that all these guys, there's sort of canonical homotopies of this into the core, which is the core of the end reduction. So you see, I mean, the preimage of one of these geodesics will be, well, at least one preimage, probably actually Brian Bowditch. So there's only one. I mean, but there's, but you have all these closed geodesics, and of course, there's going to be a whole lot of non-closed preimages. But nevertheless, this when you go really far out, you'll enclose like enough these 1,000 guys and 10,000 guys, and you do like your 0 and 1 compressions, which might kill 3 or 4 of them. But now suddenly we have like a surface of low genus, and so we shrink wrap that. And actually, there's a bunch of technical issues. I mean, one thing is that this covering space. I mean, this is just a topological surface, so there's no reason why it's not at all complete. And when you attempt to shrink wrap it, this thing might pop out of the manifold. But there's you can deal with that, because somehow if you actually sort of shrink wrap the first approximation, if you actually shrink wrap this one first, then this thing acts as sort of a barrier, and so you have this thing with like mean convex boundary. So that's sort of a hint that you could really do shrink wrap this thing. So, but there's some, but so here's actually how to produce surface of genus 3. Well, upstairs in some covering space, and now you project it into the. So now this thing is covering space of this. You project this into here, and now you've found an immersed surface of genus 3, which is at least, or smaller and less than or equal to genus 3, which is at least of the right homotopy type. Or at least it's sort of intrinsically negative curvature, and the genus is the right thing. So, but you need to show that this thing satisfies the tameness criterion. So there's 2 main things. One is to show that these things actually, well, here's a 4 things you need to know for the taming criterion. The genus bound and the cat -1 were by construction, but exiting and homologically separating, those are sort of issues. But again, we're just guided by the proof of Dick Canary's theorem, where here in the original manifold, there's you could see in the original manifold you had your sort of sequence of geodesics exiting, and you could just build this sequence, a locally finite sequence of rays that are sort of exiting from each geodesic, and so you could see these rays, or at least enough of it, to living inside these covering spaces. So by this principle of geodesics trap surfaces, that these surfaces that hitting far out geodesics means that these things sort of have to exit. And then there's the business of actually why is it homologically separating? Well, again, we're sort of guided by the proof of Dick Canary's theorem, where I mean, how do you measure what homology class this surface represents? And well, you look at a ray that goes out from the core to infinity, and you calculate the algebraic intersection number. And well, I mean, just you look at this ray, and here's the way you calculate intersection number, and you sum up over things, and the point is that, well, you just as if this thing's really far out, this surface in the end, so that there's no separation, this is not getting in between the core and some early geodesic, then you could calculate this algebraic intersection number by just using this ray, and so right. So anyway, that well, I mean, just kind of stare at this picture, and you can see that the point is that by construction, that sort of like there was this original bag here, which was the original surface, sort of, and then you shrink wrapped it, and somehow you had to worry about it popping out. But in any case, by construction, this thing was disjoint from this curve delta p its lift was already inside this bag. So and this thing wound up far away from it. So in the process, the shrink wrapping process, this thing never crossed this guy. So he's inside. So you can see that the ray, corresponding to it, sort of exits. And you actually have to worry about these other points. Some are accounted for by this lift, but maybe there's some that are accounted for by rays going from other lifts. But the point is this bag is disjoint from other rays, and basically guys are inside or outside, and the guys that are outside, you have to make a little argument that the rays going out from there contribute algebraic intersection number 0, and the ones on the inside were positive. And actually, Brian Bowditch later observed that, in fact, it turns out with this construction, there's only actually one that you really need to worry about. The others actually are non-compact, and they're all to the outside. So, right. So, anyway, that's the idea of the proof of that Danny and I had for the tameness theorem.
So, we probably have time for one question.
So is the theorem true for Hyperbolic?
What is the question? Well, he said, is the theorem true for Grove hyperbolic tree manifolds? But here you really, what are you talking? I mean, what exactly do you mean? I mean, I guess, somehow three manifold, and you're putting you have some three manifold with some metric, and so I'm not. I don't.
No, the manifold itself. Oh yeah.
Well, I think he means if this manifold, the manifold comes with some metric, and then metric, and with that metric, it's sort of like Gromov hyperbolic space. You say, is that what you mean?
Yeah, the universe. Yeah, with this.
Well, the universal cover. I mean, but the thing is, you have to be careful because the universal cover. I mean, there's simple examples of like homotopy handle bodies of genus 1, whose universal cover is large 3. So. Yeah, the universal cover is that. I don't know.
Yeah, just backing up about half an hour ago. So this shrink wrapping, can you define like this surface is shrink wrapped when it's not hitting? You cut out holes of these geodesics?
No, you just the geodesics themselves. So
you can't
so it's like this laundry line, and you throw the laundry on the line, and it just sort of has to sort of fold over the.
So it goes over the geodesics, but somehow it can't. Why does it have to have negative curvature?
No, it actually touches. Right. It might actually lie along some line segment. Because you're in a hyperbolic space.
So because the geodesic doesn't have positive curvature, it can't have positive curvature.
I mean, that's a heuristic thing I'm giving you. And, but so then in real life, I mean, there's sort of the thing you just need. Actually, Dennis mentioned this at the 5 years ago. When, Thurstons construction, if you have like an end geometrically, n homotopy equivalent to surface cross R, and you have like an embedded geodesic, and this embedded embedded simple closed curve in the surface, and then you just homotop it out to a geodesic, and sort of Thurston's construction of a pleated surface along that curve is, in some sense, to start with, you can think of it as maybe just being pleated, being shrink wrapped with respect to that curve. So there's so it's sort of like bent along, exactly like curves going surface close over the laundry line.
In Theorem, you say that it needs to be 2 compressible, but in your slides, when you say shrink wrap, you say 0 and 1 compressed.
Oh, so I said before you you have a surface that, just a nice topological surface with all these geodesics inside of it. Before you could shrink wrap, you have to get a new surface by just compressing, by doing the 0 compressions and the 1 compressions.
What about the 2 compressions?
Oh, 2 compressions are okay. So being 2 compressible, being 2 incompressible means that 1 incompressible, whatever, I forget the terminology already. But the point is that any compressing disk has to intersect the geodesics at least twice. If it intersects once, you sort of imagine like a long neck with the geodesic in the middle. When you start shrink wrapping, it's sort of like pinches off.
So it's just a definition. So 2 incompressible means there's no 0 or 1.
Yeah, sorry. 2 incompressible means there's no 0 or 1 compression.
Thank you.
Yes.
Okay, so I think we're kind of out of time, so let's thank the speaker here.